In this video, we're going to discuss combining reactions and how that affects our equilibrium calculation. One thing we need to discuss is that if you have a reaction of A going to B, and you get some equilibrium constant where your concentration of B divided by your concentration of A is equal to your constant. However, the reverse reaction, if we had just written it the other direction, well, this equilibrium constant, we'll write prime here, would be equal to concentration of A divided by the concentration of B. We've just flipped our ratio, which means all we need to do is flip our original constant. Remember, everything's always over 1, so 1 over the original constant is going to be equal to the reverse constant. If you reverse a reaction, the equilibrium constant for the reverse reaction is just the reciprocal of the original direction's equilibrium constant, because all we do is change which value is on top and which is on bottom. Say you had something like 5 over 1, your constant was 5. Flip it to 1 over 5, your constant's 0.2, which is, well, 1 divided by 5. And so if you change the direction of a reaction, there's no extra work that has to be done for its equilibrium constant. The constant doesn't change, just how we wrote it changes. Did we give the original or its reciprocal? This becomes important if you're using equilibrium constants and some Hess law calculations. Let's say I have a reaction of 2CO gas plus O2 gas in equilibrium with 2CO2 gas. In this case, this has a K for reaction 1 equal to 3.3 times 10 to the 91. This is extremely favorable. Carbon monoxide reacts with dioxide and make carbon dioxide quite readily. We'll also have reaction 2, which is 2H2 gas plus O2 gas makes 2 water gas. If we do this at elevated temperatures for these K values, then here for reaction 2, this is 9.1 times 10 to the 80. It is also extremely favorable to make this product. If we're using these to find a reaction of water gas plus carbon monoxide gas in equilibrium with CO2 gas and H2 gas. So if I have water and carbon monoxide interact, well, there's a strong driving force to make CO2, but that would free up dihydrogen. Let's find this K value. Well, this is a Hess law. I have 2 reactions I need to reorganize to make my third reaction. I have water over here on the right in reaction 2, but I want it on the left. So I need to flip it. I need to say, hey, there's a reverse of 2. That is 2 waters in equilibrium with 2H2 gas and an O2 gas. I made the water on the correct side. I have this oxygen that I don't want, though. I have one of them, and hey, I can get rid of it using equation 1. That'll even give me CO on the correct side and carbon dioxide on the correct side. So I'd probably combine it with equation 1 then. 2CO gas plus O2 gas in equilibrium with 2CO2 gas. Combine those, cancel the things that cancel. I'll get 2H2O gas plus 2CO gas in equilibrium with 2 CO2 gas and 2 H2 gas. Only thing we've done wrong so far is we have twice as much as we want, which we'll adjust that in a second. How does this affect our K values so far? Well, if you add two reactions like in Hess law, you multiply their Q or K values. Since we're working with equilibrium, we will multiply our K values. Well, what are our K values, however? Reaction 2 got flipped around. And so really the K value here is the K prime for reaction 2, which is equal to 1 over the original. So that's going to be equal to 1 over 9.1 times 10 to the 80. For reaction 1, well, that was the same. So constant of equilibrium for reaction 1 is still just 3.3 times 10 to the 91. To find our K for our combined reaction, that's going to be equal to Kc2 prime times Kc1. That's going to be the modified constant for reaction number 2, where we use the reciprocal, times the unmodified constant for reaction number 1, since we didn't need to change that. And so at first, this would be, hey, our combined equilibrium constant here is going to be 3.3 times 10 to the 91 divided by 9.1 times 10 to the 80. So this times that. Don't forget your parentheses when you calculate, but our Kc for our combined reaction should be 3.626 times 10 to the 10, except we had a problem. We're still double. And we didn't want to be double. So we haven't really solved the actual constant for the reaction we want yet. We found it for this times 2 reaction. Well, think about what that would do to our expression. Normally, K is going to be equal to the products to its coefficient. So CO2 squared, H2 squared, divided by the reactants to their exponents. They're all squared, but the reaction we want, one up above, should be to the first power. So the real value we're looking for has each of those to only the first power. This is a consequence of having twice as much for each reagent in our purple expression there. Well, I could just divide these by 2. If I do that, that gets rid of the doubling. Everything is reduced to half as much, and it gives us the reaction we want up above. How does that play out in a calculation? When you have something that has all the components squared, you can write that as the individual things not squared, but the whole thing squared, where you would have to distribute it. So what we find is that, hey, I could have the actual reaction I want. Problem is the present value that I just found earlier is really that squared. So how do I get down to just the reaction I really want? I would need to square root both sides. The square root of this enhanced 3.626 times 10 to the 10 would actually equal the expression that we want. Another way to think of this, when we add our equations, we multiply our K values. So if we do multiplication or division to our equation, we have to do the same power to our K values. So if I want to divide the reaction by 2, what I'm really doing is I'm taking my K value we calculated to the 1/2. The square root, which is what we see right here. If I'd had to divide by 3, I'd do to the 3rd root. If I'd had to multiply by 2, I would have squared it. If the Hess law produces an equation where we don't have the right coefficients and we have to scale our coefficients up or down, whatever we multiply or divide by, we have to take the exponent version of that to our k-value that we calculated. And so really, for the coefficients of 1 values we have, my k-value would really be 3.626 times 10 to the 10 to the 1/2. What we'll find is that our real k-value for the actually indicated reaction with coefficients of 1 is 1.9 times 10 to the 5. And so in this example, there's 3 key components. You can combine reactions, as Hess law has done, to make a target reaction. If you know equilibrium constants for the individual reactions you used, you can multiply them to find the equilibrium constant for the target reaction. If you have to flip one of your reactions around in the Hess law, well, then your new equilibrium constant is just the reciprocal of the original direction. If you have to scale one of your reactions, doubling or halving, you have to do that as an exponent change to your equilibrium constant. It's possible we could have modified each equilibrium constant individually before. We could have divided each reaction by 2 originally so that we didn't need to do it at the end. It doesn't matter whether you do it to each individual reactions before combining them or do it to scale the combined reaction after. Math will come out the same. But when we add our reactions together, we multiply our k-values together. Flipping a reaction, we use the reciprocal of our k-value. Multiplying or dividing our reactions means we have to adjust the power to which we modify our k-value.